Hey, welcome everybody to our first SciSchool Hangout. We've got Brad Tucker from Mount Stromlo Observatory at the Australian National University, and he also works at the University of California in Berkeley. He's actually got a lot to do with NASA, and he runs his own satellite project now. So you're in some very good company, Year 10 students from Parklands. Brad is an astronomer, and he's going to be giving you a bit of a presentation to start off with this morning. And then once he's finished his presentation, we'll hand it over to you, Year 10 students, and you'll be able to ask him as many questions as you like and have a great discussion about the science that he does. Okay? So take it away, Brad. Over to you.
So, as Sam said, I'm an astronomer, and one of the places I work at is Mount Stromlo Observatory. So since I can't see you, just either moderately or just yell out, what do myself and astronomers do? What do we do at observatories? What do astronomers do for their job?
Go to the moon.
The moon, yeah, what else?
You study space and how it works.
Yeah, that's right, we study space and how it works. What else?
The speed of something in a given direction.
That's right. So what else would you think we would study, but you might not think about it right away? I'll give you a clue. It's up during the day.
Stars.
The sun. And what are we standing on?
Sun.
No, the sun, but what are we standing on? We're not standing on the sun. The Earth, that's right.
Planet.
A planet. So yeah. So astronomers, we want to study everything from the ground up. Astronomers study planets, and the best way to study how planets work are to study our planet. We study other objects in the solar system like moons and asteroids and comets. We study stars, and the best star to study is the sun. But then people study galaxies. So galaxies are groupings of stars. So our galaxy, which is called the Milky Way, has about 300 billion stars in it. And then other people like me study the whole universe, and that's everything inside our universe, all the galaxies, all the stars, all the planets. So we can estimate our universe has about 175 billion galaxies in it. And each of those galaxies has about 100 billion stars, so there are lots and lots of stars out there. And one of the things just announced this morning by the Kepler Space Telescope, which is actually going to be the telescope I take over to do my science, found that pretty much every star in the night sky has at least one planet, and we can estimate there are probably about 10 to 15 billion planets the same size and composition as Earth and the same distance to their star. So 15 billion potential planets that can host life just in our galaxy. And there's 175 billion galaxies. So in short, there is a lot of stuff in the universe. So I'm taking over Kepler to do my own science, and what I'm going to do is study how stars explode and how black holes swallow stars. And what we'll be able to see, if you guys can picture a nuclear bomb going off, you get the shock wave, the pressure coming out before the terrible part comes. Well, stars do that too, and with Kepler we can see the shock wave go through a star before it blows up. And we can see the moment a black hole eats a star, even something just the size of our sun. And when black holes eat things, they actually rip them apart. So what I'll do is I'll give you kind of an overview of the things that I'm working on and other astronomers are working on. And if you have any questions at any time, try and yell out, and we'll try and do this in an orderly manner. So can we see this slide?
Yeah.
So this isn't a real image. This is an artistic illustration by the European Space Agency. And this is showing all of the satellites from 3 years ago that existed in space. Now, we have a lot more satellites up there, and this isn't showing the military satellites. There's probably at least 5 times as many up there as this image shows. And one of the problems that we're starting to have are we're polluting space. We're polluting the area right near Earth. And one of the things and problems this causes are sometimes space satellites can collide. Other times, there's accidents. About 3 years ago, an astronaut on a spacewalk dropped a tool bag that consisted of a spanner and a screwdriver. Well, that spanner and screwdriver are now orbiting the Earth going 15,000 kilometers an hour. You can imagine that as an astronaut or your expensive space satellite, you would not want to be hit by that. There was actually in the news a couple months ago. The International Space Station had an emergency spacewalk because there was a leak in their fueling tank, and that was caused by a small piece of metal debris running thousands of kilometers through their expensive satellite. What we're trying to do is solve the space junk problem. So when space satellites are broken, or when we drop things in space, or when space satellites die. So what we do is we launch a very powerful green laser into the night sky, and we can track objects that are 1 centimeter wide, 200 kilometers above the Earth. What the laser does is the laser goes up into space, it hits an object, reflected back down into our telescope, and then we can track it. We then update a catalog, and we can tell astronauts and satellites to get out of the way if there's something potentially hazardous. What we're working on improving is in tuning the laser to be able to track things down to 4 millimeters wide. Anything smaller than 4 millimeters will either burn up in the Earth's atmosphere right away or go out into outer space. It won't establish an orbit around the Earth, so we don't care about those. What we're also trying to do is to be able to tune the laser so when it hits the piece of space junk, the metal debris, it either deflects it so we knock it out into the solar system and outer space, it's not a problem, or it vaporizes it altogether. So that's one of the things that it's not quite as normal you think with astronomy, but it has to do with space and space travel that we're working on. So this next image, again, is an illustration, and this is how we think the Earth and Moon formed. The Moon, we believe, wasn't actually a separate object, but was formed due to a collision of a smaller object running into the Earth. So if you can imagine 4.5 billion years ago, there was a kind of molten rock, and they were forming planets. So you have a larger object forming the Earth, and a smaller object forming something that we believe now is the Moon. They ran into each other, and when this collision happened, all of these rocks and all this molten lava ejected from the Earth and wrapped around this object to form the Moon. And this is because this is one of the big successes of the moon landings. What we realized is that the rocks on the Moon are very similar to the rocks we have here on Earth. Now, all of the rocks that we can measure in the solar system, the rocks on Mars or even Venus, are quite different, but the Moon is really close to the Earth. The other thing we've noticed, and you can see this with your own eyes, if you go out on a night when the Moon is almost full, you guys can see lighter areas and darker areas of the Moon. Well, those darker areas are actually the most recent volcanic lava flows. Now, those haven't happened for millions of years, but the Moon actually did have volcanic activity just like we have on the Earth. And those gray areas are actually, you can imagine, volcanic lava fields that are hard rock, and they actually have less craters because it's a harder new material. So this is an image of our solar system. Now, it's not to scale, but what is wrong with this image? Any ideas? Pluto, that's right. Pluto's on it. Why is that wrong?
Pluto isn't classified as an actual planet. It's a dwarf planet.
Exactly. So Pluto's classified now as a dwarf planet. So why was Pluto demoted to a dwarf planet? Or, the same question, what is the difference between a dwarf planet and a regular planet? It's a little bit tricky.
Is it because it's really small?
It does have to do with its size, but it's not specifically because it's small.
Does it also have to do with its orbit?
Exactly. Good answer. It has to do with its orbit. So this image doesn't show it. Exactly. That's a good answer. It's a tough question. We've seen the orbits of the planets, and have you guys have seen how Pluto actually crosses into the orbit of Neptune and sometimes into the orbit of Uranus?
Yeah.
Well, that is because Pluto actually isn't in a stable orbit. And it's because Pluto has 5 moons. 4 are pretty small, but 1 is significantly large, and that's called Charon. And instead of Charon orbiting Pluto like our moon orbits the Earth, Charon and Pluto do a dance. So they actually orbit around a central point between the two. And because of that, Pluto can't control its orbit around the Sun, and it's actually pulled by Neptune. So Neptune, therefore, affects the orbit. So you can imagine why Pluto is tumbling around with Charon, and it has this irregular orbit. So the definition of a planet is it has to orbit a star. So this is a critical point that sometimes is overlooked. What in our solar system doesn't orbit a star? Any ideas? What doesn't orbit the Sun? Sorry? The moon, exactly. The moon orbits Earth, the moons of Jupiter orbit Jupiter, and so on. Those are satellites, natural satellites or moons. The second is it has to be round. And this is a very important physical condition. In order to be a planet, you have to have something called angular momentum and hydrostatic equilibrium. That's a very technical thing you'll get to learn in university. But what it means are planets pull themselves into soccer balls, while everything else, like asteroids, which do orbit at the star, become potatoes. So if you're a soccer ball, you're a dwarf planet or a planet. If you're a potato, you're an asteroid. And then the third criteria is the orbit. It has to have a planet has to have cleared its path of its, or it has to dominate its orbit. And so because of this, we now have 8 planets and 5 confirmed dwarf planets, but most likely we're going to have more. So this image shows while we have Pluto, there's actually 8 other objects around Pluto and further that have similar properties. So we have something that's bigger than Pluto called Eris. We have things that are smaller. We have things that have moons. We have things that don't. There are lots of these objects out there. And the important part of this is we don't understand why these objects are. If you look at our solar system, we have 4 small rocky planets on the inside and 4 large gas planets on the outside. Through simple physics and maths, we can explain how those 8 planets come together in the way they do. But we don't understand how we get small, cold, rocky things similar to the inner planets on the outside of these large planets. It makes absolutely no sense. And so even though Pluto is not technically a planet, it's actually one of the most important objects in our solar system. Now, as I said in the beginning of the talk, we believe that at least out of every star in the night sky, at least one has a large planet. Well, the large are planets the size of Jupiter or larger, and those are the only ones we're being able to detect. We can now detect Earth-sized ones, but if you imagine all of these objects are smaller than the Earth, so we have 8 planets, 5 dwarf planets, plus all these small things, think how common these objects are in the universe. Planets and dwarf planets should be very, very abundant. So I'm going to turn to something kind of different, and this is something I work on. So let's look at our whole universe. Our universe is 88 decillion, which is 88 followed by 18 zeros, kilometers wide. So it's very big. Light from the Big Bang, which is what we believe caused the universe to expand, takes 13.8 billion years to reach to us. So it's very far. Now, one of the things that I do is trying to figure out what is in the universe, which seems like a simple question, but it's very difficult. You guys should have all seen this image, right? A periodic table of elements?
Yeah. Yes.
So, if we think of all of the stars, all of the gas, all of the planets, all of the rocks in our universe, and all of the elements that we have, how much of everything in the universe is made up by the periodic table of elements? So does the periodic table of elements make up 100% of everything in the universe? 50%, 10%, 0%? Any guesses?
Yeah, 100%.
Way less than 100%.
No idea. 10%?
40, maybe.
Less than 10%.
Wow.
2.
Less than 2%.
-3.
No, it's a positive number. It's not a trick question.
0.1.
It's close. 0.5% of the universe is made up by the periodic table of elements. 99.5% of the universe is not found on this table. Firstly, these aren't all the elements. The real periodic table of elements looks like this. And that is because, as we can say, elements can actually mutate. So we learned that an element has equal number of protons and neutrons. Well, we can actually alter that and have a similar element that has different number of neutrons. So we can actually get oxygen, which has 8 neutrons and 8 protons, having anywhere from 8 protons and 1 neutron all the way up to 8 protons and 14 neutrons. And that actually alters and mutates the element. I'm not going to make you learn all this, but even if we think of all of this stuff we can do, and we can study these on the Earth, that only actually makes up 5% of the universe. 95% of the universe is stuff we have no idea about, with about 70% being something called dark energy and 27% being something called dark matter. Now, the two aren't related, we're just not very creative. So, firstly, dark matter. This is an illustration, but if we have a galaxy and all these red, orangey bits are stars, we actually have a diffuse distribution of matter that we can't see with telescopes, but we can see its effects. And we can see its effects by measuring how fast galaxies spin and by weighing galaxies. So this is a simple plot, and this is an experiment we can all do either right now or probably later. So everyone, I assume, is spun in a desk chair, right?
Yeah.
So what happens as you move your arms from inside, so if you hold your arms close to your body and you move your arms outward, what happens as you're doing that as you're spinning?
It pushes the other people next to me away.
So you get slower, that's right. And as you pull your arms in?
Get faster.
That's right, you get faster, you speed up. And this is called the conservation of angular momentum. When you concentrate your mass, you can spin faster, but when you distribute your mass over a larger area, you slow down. So if we look at a galaxy, and we can plot the distance of the objects across a galaxy and how fast they're moving, the objects on the outside of the galaxy, because we spread more mass and more weight out there, should be moving slower than the objects inside our galaxy, just as we spin in a desk chair. But and that should look like this dashed line A. But what we found is that actually parts of the outer galaxy are faster than the inner galaxy. Now, this either means that we're weighing galaxies wrong, or that our basic physics that explains how we spin around in a desk chair is wrong. Most people tend to believe that our physics is right because we can easily calculate all these sorts of things on the Earth of how we spin and move. So it has to be that we're actually missing something. And what we believe we're missing is something called dark matter. And the idea is either a macho, like Arnold Schwarzenegger, or a wimp, which I call my chemists. I'm just kidding. So, a macho stands for massive compact halo object. And what we thought, and so this is kind of the astronomy solution, was if we have lots of stars that at the end of their life don't have any light. So we weigh galaxies by counting up all the light and then kind of doing an estimation of its weight. But if we have lots of stars that don't have any light, that are at the end of their life cycle, or stars that have collapsed and formed neutron stars or black holes, we might be missing this light and therefore underestimating the weight, and it could solve the problem. Now, to solve this, what we did is we pointed a telescope at a neighboring galaxy called the Large Magellanic Cloud, and if one of the cool things that Einstein predicted is if you get a massive object moving in front of light, you can bend light. So through mass and gravity, you can actually change the shape of light if you have a large enough object. So we pointed our telescopes at this neighboring galaxy, looking for bends in the stars we can see. What we determined is we found a few of these objects, but we are missing about 300 trillion of them. So we are a little bit off in trying to solve this problem. The now solution is something called a weakly interacting massive particle, or a WIMP. Again, astronomy and physicists are not creative, so that's why. A WIMP, so if we imagine protons and neutrons, those are made up of smaller particles. There's lots of these small particles that exist, and there could be one that we haven't found yet that is really heavy but doesn't have light. And if that's the case, it could make up a lot in the universe and a lot in the galaxies and explain this problem. So the Large Hadron Collider, which is this experiment in Switzerland, have you guys heard about it at CERN? No. So it's what's called a particle accelerator. So you accelerate at nearly the speed of light. So you send two particles traveling 0.9995 times the speed of light. You ring them around and then you smash them into each other and see what happens. And what you're trying to see is if you can create high enough energies to find smaller particles. So what this experiment's doing is trying to find these small particles if they exist, and this could solve our problem. We've been unsuccessful as yet, but we're still looking. Now, all of that only makes up 27% of the universe. The other 70% is something called dark energy, and that's really what I work on. So the universe started with a Big Bang, and that caused the universe to expand. What we thought was as the universe was expanding, as everything was moving away from each other, gravity should slow this expansion down, stop it, and pull it back together. What we found, though, was the exact opposite. That the universe, instead of slowing down, is speeding up. So that means the universe is growing more today than it did yesterday. It will grow more tomorrow than it is today, and so on and so on and so on. And this will cause the end of the universe in one way or another. Now, we do this with two ways, something called standard candles and standard rulers. So if you know the brightness of an object, you can measure how far away it is by how faint it appears. And you can do this experiment at home. If you look down your street and you see all the street lights, the further street light will be dimmer than the one right next to you, and that's because light travels in all directions and it dims as it goes away. If you can measure the brightness of the bulb and the light right next to you, and you can calculate the brightness of how faint the far away one is, you can compare the two and figure out how big or how far away it is. Likewise, if you know the size of something or the distance between something, because just as the horizon, things appear smaller on the horizon, you can calculate the distances between something near and far and calculate how far away that is. You can calculate the distances, you can calculate how fast things are growing, and therefore figure out what the universe is doing. Now, the way we do this is we use stars that blow up. So this bright object in the middle, so this is the picture of the galaxy, and that bright star in the middle isn't a star, it's a star that blew up, and it is equivalent to 100 billion lightning bolts. So if you imagine how powerful one lightning bolt is, how bright and energetic, one star when it blows up is 100 billion. And it can be brighter than actually all the light, all of the stars, the hundreds and billions of stars that make up a galaxy. There are about, if you figure all of the stars in the universe, there are about 30 stars that blow up every second. So there are about over 3,000 to 4,000 stars that have blown up since we started talking. This means that they're very good tools to find and use to study the universe. So can we see, we have two images side by side. Can you see this?
Yeah.
Okay, so it's going to be a little bit tricky. I want you to find the star that blew up. So on the left, I'll explain, we have an image, and then on the right, we took another image 3 days later. And in here, there is a star that blew up. There's differences between the night variations. So some objects appear dimmer, not because they're actually dimmer, but things like our atmosphere and the moon reduce the quality of our images. So can anyone see where a star has blown up? So it will be present in the right image and not in the left.
The one in the top right corner.
The very small one or the bigger one?
Small one. Yeah. Small one.
So the far top right corner, no, it's close there.
It's the one that's a little bit to the left. It's next to the really big one, but up right.
So you got the really big galaxy towards the top left-ish, but then there's one to the top right of that?
Yeah.
Yeah, that's exactly right. So if we subtract the two, there's a green circle where a star has blown up. So that's a good eye. There's actually something else that changed, and this little bright circle galaxy in the middle of the image, there's actually a difference, and that difference is we have just detected a star, a very large star that was swallowed up by a black hole and ripped apart and then ejected.
Oh.
So black holes do take in and suck a lot of things, and we can see this process. Now, one of the cool things in how we use these supernovae as tools are we can figure out the actual star that blew up. So this is a supernova, a star that blew up in our neighboring galaxy, the Large Magellanic Cloud. On the left is an image of the explosion just a day after it happened. And on the right, there's an arrow pointing to a star. And that image was taken a long time before the star blew up. And what we found was that star where the arrow is has disappeared. So we can actually calculate the exact size, temperature, and mass of that star that blew up, and therefore figure out how bright it is and use it to measure the universe. Because if we know how bright something is, we can measure how faint it is that far away, like in the images I just showed. We can calculate how fast the universe is growing. But another cool tool, and we'll just end on this, just a few more slides, is that, well, firstly, we can see that the universe is actually accelerating. So if we plot velocity versus distance, changing in velocity versus distance is acceleration. If the universe wasn't accelerating, so as we went further in the universe, as we went further to the top, if the universe was just constant, we should see a flat, straight line. But this curve is real. That shows that the universe is actually speeding up as the universe is growing. And it's not just a factor of our supernova. we can see sound waves from the Big Bang. So I said there's two ways to do this: standard candles and standard rulers. Standard candles are using supernova when we know how bright they are. If we know something how set distance away, we can use them as a standard ruler. When our Big Bang happened, it made a vast, quick expansion. And it made essentially a sonic boom. So as a jet goes, and it goes faster than the speed of sound, you hear that sonic boom. Our universe did that when it was really young. And that sonic boom, just as you were to drop a pebble into a stone, you get ripples, right? So as sound waves, you get echo and then echo. These sound waves continued through the universe, but as the universe cooled and started to form stars and galaxies, formed waves of galaxies. So we don't have galaxies evenly distributed around the universe. We actually have waves or ripples of galaxies traveling through the universe, stuck on the sound waves from the Big Bang. And this very technical plot on the right shows exactly that. So don't worry about what it says, other than you see this big peak and then these ripples. Those ripples are the real ripples of galaxies coming through the sound waves of the Big Bang. And so through this tool and through the exploding stars, we can measure that the universe is growing faster than it can sustain. So what will this mean for our universe? At first, we thought we'd have the big crunch, when gravity would slow the universe down and pull it back into one, a reverse Big Bang. Again, we're not creative. Now, we know that's not going to happen because of this dark energy, this thing that's causing the universe to grow faster and faster. And there can be two consequences of what happens. One that's really cool and one that's very boring and kind of sad. The cool one is called the Big Rip, and as you can imagine, it's a rip. What this is as the universe grows, if it grows so fast, it will actually rip itself apart. The fabric of the universe, so your dimensions of X, Y, and Z and time, will rip apart. And there are two main theories about what will happen because of this. So one of them is, just as cells can divide to form two new cells, some people have hypothesized that when the universe rips, it actually rips into two new identical universes that then grow on to form other universes. The second idea is, if the universe were to rip, the energy released and contained in that ripping would be the exact same amount of energy as the Big Bang, and then therefore give birth to a new universe. So it could help explain how our universe was created and give an explanation of what's going to happen to our universe. Now, the other theory, which is very sad and I don't like, is called the Big Freeze. And what this means is, if the universe is growing so fast, everything just gets pulled apart. So at some point you'll look up and we'll only have one galaxy in the night sky. We'll continue until you can only see our star. There will be no stars you can see. Then the planet will be isolated, and then actually elements will be pulled apart, and you'll only have elements, and then you'll only have protons and neutrons. And this continues and so on until nothing can actually be together and nothing can form. So the universe just freezes itself out, what we call the Big Freeze. But because that's boring and sad, I don't like that, and I go with the Big Rip. So our universe will end at some point. This isn't going to be for billions of years. We don't know which option it's going to be. We don't know what 95% of the universe is. But that's okay. These are all awesome, cool things to study. So I think what I'll do is I'll end there. And do we have questions?
Hey, I was just wondering if the Big Rip could have already happened, and it's like in process.
That's a good question. Because it's the actual time of the universe, we would know about it. It's kind of like if you're driving the car, if you're driving down the road, and, well, you might not know if a part of your engine breaks, but you'll know if your car disintegrates. So it's kind of, there will be such a big event that we'll have to know about it. It's a good question, but related to that, there's actually something related to that. There are things in our universe that we will never be able to know because the universe has grown so much. So the speed of light is finite. It has a speed.
Yep.
If the universe has grown so much, light from the very beginning of the universe will never catch up to us. So there could be some place in the universe with a big neon sign saying this is the answer to every single question you have. You never have to study anything else. But because it's so far away, we'll never see that sign. Just as there are actually things in our universe we see now that we'll never be able to see in about 2 billion years.
I have a question.
Sure.
This time we've been using like ticker timers to graph acceleration, and we were just wondering how does acceleration work in space?
So for spacecraft?
Yeah, or like any space objects or any sort of matter or anything.
Well, okay, so that's a good question. So natural objects have kind of different ways they move than man-made objects. Natural objects actually use gravity in order to spin. So, for instance, the sun is slingshotting us around it through its gravitational pull. Man-made objects, once you go out of the Earth, the speed you're leaving the Earth is pretty much the speed you stay at, unless you use thrusters or something like that to contain. So if you can get something near the speed of light going out of the atmosphere, you will keep on traveling near the speed of light through the rest of the universe. And you can actually use solar panels to use wind from the sun to blow you further. Does that answer your question?
So if that object keeps traveling, yes, but if that object keeps traveling, would that object eventually get pulled apart, or would it just keep traveling and stay?
It will just keep traveling. There are all the satellites that we sent out 30, 40 years ago, they're just keep on going. Unless it runs into something, which is very unlikely because space is pretty wide, it's just going to keep on going. And that's that. It's actually really hard to get something to return back to the Earth. We've only landed and successfully returned one object from space.
Okay. What kind of equipment do you use?
I'm sorry?
What kind of equipment do you use?
So I mostly use big telescopes, both on the ground and in space. So telescopes, we use telescopes based on how wide their mirror is. So the largest telescopes on the Earth are 10 meters wide, meaning their mirror, the thing that collects light, is 10 meters across. If your eyes were 10 meters across, you can see exactly the same as that large telescope. But you'd also have a big head. So, the other thing that we use is telescopes in space. The reason telescopes in space are good are we don't have the effects of the atmosphere, so the atmosphere blurs images. So if you look into the night sky, stars twinkle. The reason stars twinkle is the same reason that there's turbulence in airplanes. Differences in temperature and wind cause the atmosphere to shake. So we can't control that. We can only measure its effects. If we send a telescope into space, we don't have those problems, but we also can't get to it. Also, because you can point and have pretty much 24 hours of nighttime, you don't have to worry about the sun. So I use a lot of telescopes all over. Other astronomers use radio telescopes, which use the radio wavelengths to study stars. So we can actually study stars using radio telescopes, X-rays, just like we have X-rays on your bones, infrared, which is the similar stuff that you see on the cricket FLIR vision. We can look at stars, and all these different colors of light tell us something different.
Okay.
Hey, how's it going?
Good.
Just wondering, what are your degrees, and
How long did it take you to study them?
That is a great question. So in the U.S., university is 4 years, as usually 3 years in Australia. I got 3 degrees as an undergraduate in the U.S. I studied physics, I studied philosophy, and I studied theology. So they're all a little bit different. To be an astronomer, you then have to either do an honors degree in Australia or a master's degree. And the cool thing about that is it's not like studying in normal university or normal school. You get to learn how to be an astronomer or how to be a scientist or whatever. You take a question and start to learn how to do it. You also get paid. I actually skipped that stage and went straight to a PhD. And a PhD is really an apprenticeship in being a scientist. You have your project, and the thing you're supposed to do is find out something that no one else knows. So it's not like you can go into a book and look up the answer. You have to find the answer. So it's a little bit daunting, but that's okay. So it took me 4 years, but I actually did pretty much 2 PhDs. I did a PhD in astrophysics and then a PhD. So I did a PhD in astrophysics at the ANU and then a PhD in cosmology at Harvard. But I did it at the same time. That's a little not normal.
Wow.
Yeah, most people only do one. You get paid during this whole time. Again, when I did this, after I did the PhD, you get to become an astronomer and get to have lots of fun. So it's about 8 years from after you leave. 8 years after you leave high school.
I was just wondering what you're currently working on.
So I'm currently working on, that's a great question, what we're trying to do. We're trying to figure out exactly what this dark energy is that is causing the universe to accelerate. One theory is actually something that Einstein came up with. So when Einstein came up with this theory of relativity, he was a great mathematician and great physicist. His equation, when you actually get to study it, essentially says 1 equals 0. Now we should all know through basic maths, 1 does not equal 0. So he said there has to be something that makes 1 minus 1 equal to 0. And he called this minus 1 something called the cosmological constant. So if 1 is gravity, you would have something that's anti-gravity, essentially, to balance the equation. But he said it was so crazy, it was even crazy for Einstein, he didn't publish it and didn't actually let other people know for a long time. He called it his biggest blunder, and he was ashamed of it. It almost seems, though, what we're seeing is exactly what he predicted. Now, we're trying to figure out whether it's that or something else called quintessence or phantom energy. And this is actually a new source of energy or force that changes with time. So the weird problem in this whole thing, with gravity, the further you are away from an object, the less gravity pulls you. So Jupiter is pulling on us, on the Earth, but not that much, and the sun's pulling on us very strongly. The dark energy, or whatever is causing this acceleration, has the same effect no matter where you are. So if dark energy was gravity, we are being pulled by the Earth would be the same as being pulled by the sun, would be the same as being pulled by Jupiter, by distant galaxies. It actually changes with time. Now, if this doesn't make sense, then you understood it because it doesn't make sense to us. And this is what I'm trying to figure out.
All right.
Okay, guys, we'll wrap it up there. Thank you very much, Parklands. You've been fantastic asking questions and answering questions as well. You did very well when Brad put questions to you. Thank you very much, Brad, for for being our featured scientist on our first SciSchool Hangout. Your talk was fantastic, and you really got the guys involved. I think that there's someone at Parklands who has one final thing to add, and then we'll wrap it up.
Great.
Thank you, Brad Tucker. On behalf of Parklands Christian College, we would like to thank you for taking time out of your busy schedule to provide us with informative knowledge about science. Thank you.
Thank you.